are problematic in this kind that we need Lipschitz nonlinearity. We have two ways to solve this now. We have once the linearizations around the equilibrium, then we really get a really Lipschitz nonlinearity, but that just gives us ideas for the behavior around the equilibrium. So this is the one reason. If we have this, we get the existence of a mild solution. I will come in a moment to the definition of mild solution and weak solution, because maybe we are not familiar to. You just need some ideas of the nonlinearity have to be Lipschitz. We need some linear growth conditions, and also for the noise term B. That's important, especially because we have here a white noise. So we don't have a colored noise. We want to use a white noise. So that's important. So we need this, but we get this. For the other case, we can also simplify our system by using an adiabatic simplification. Then we can also use and find a mild solution. Unfortunately, we cannot find for the existing system. So I talked a lot. I said I want to mark out what's the important, what's the difference, because I know a lot of persons here are really experts in PDEs. So I want to mark the difference between the impact of noise of system behaviors. That's why we have here just modeled once our system. It's not with finite element. Until now it's just with finite differences. So I marked it here. I put it just the factor who was here before. I put it down to 0, so I have no noise. I have just a normal deterministic system. So if I now put the noise to 0, I get just waves. I just see oscillations occurring in time, but not in space. If I now include the noise part, so I set my alpha to something similar, like 1 point, something similar. It seems to be really small, but it's just because we made the system dimensionalized. That's why it seems really small. Then we can see already a big difference. And that's also like behaving close to elliptic seizures. So here we can really see oscillations that occur now small. We can do it harder, but small. We have like a kind of traveling waves that oscillates both in time and in space. So I just wanted to put here this slide because I think a lot of you are really familiar with weak solutions. So I just do it here. I didn't mark it out, that should be a test function. So that's the normal idea of what we use. I already marked here that we need this concept, or we can use this concept of weak solutions for linear SPDEs. For our case, we will later need the formulation of mild solution, which is a little bit more rough, which allows us to also get in touch with nonlinearities, or you can also use weak solutions for nonlinearities, but if the nonlinearities are highly difficult, and also if you're dealing with white noise, as our Wiener process has the covariance matrix as the identity, then you really need the mild solution. And then the solution can be expressed in this form. That's why we also need our semigroup. The ST here is a strong continuous semigroup, and we can write a solution down like this. As so far, I want to come now to the linear stochastic wave equation. So because the wave equation part is the most difficult part in our system, and it's well studied, but it's also still an interesting idea to think about. So just to briefly come to the same point, we have the linear stochastic wave equation here with Dirichlet boundary conditions. And yeah, here I marked just a little bit what we are talking about. This Wiener process can be a cylindrical Wiener process. Then we have the identity as the covariance matrix, or it can be just a trace class operator. Then it makes everything more easier, but then we have colored noise, and we get like the normal representation. To come back to my formulation, to write it with a dx or something, I just transform this second order partial differential equation into a system of two first order equation, and that's what I get. That's what I get here. So just say x, the first is u, and the second part is the derivative of u. Then you can just transform it into this kind of system. We work all the time, I have to point it out, we work all the time on the convex polygonal domain. That's important because we want to show like the existence of a solution, and therefore we need this domain. So especially in dimension 1, we have an interval and things like this. So what's new, well, not new, already 10 years old, but which was not studied before, was the Sobolev, the spatial Sobolev regularity as an idea for the existence of solutions. And that's what Kovac, Larsen, and Sepane introduced in their paper. They introduced such a kind of hybrid condition here. And they said if just this reason, so it's just crucial depending on the noise. If there exists a weak solution, or in this case, the weak solution is also a mild solution, exists, it's just crucially depending on this. So when does such kind of solution exist? And there are two possibilities. And the first possibility is that the operator Q is trace class. So the operator of our Q-Wiener process. If it's trace class, it's really simple, because then, okay, you can just put B2 in this in this condition, put to 1, then you get just the operator, and then you use just the definition of the Hilbert-Schmidt norm. The Hilbert-Schmidt norm is the trace, and if it's trace class, the trace is finite, everything perfect. But now coming to the more difficult part, which is our part, the case of space-time white noise. In the case of space-time white noise, we have the problem if we write down the Hilbert-Schmidt norm in with the possible identity, we get here the Laplacian operator, and here the eigenfunctions, the normalized eigenfunction, which are some kind of scale of the science function. This is now the computation for the one-dimensional case, because for the one-dimensional case, I also get the eigenvalues of the Laplacian, and I can put it out. And I discover I can put beta to something smaller than 1/2, and I get the existence. So the problem is, if we now get to a higher dimension, for example, to dimension 2, then the eigenvalues of the Laplacian behave asymptotically like what I put there, k. So behave like k over 2. Yeah. 2 divided by d. And yeah, that's like the asymptotic behavior of the eigenvalues. And if you have like this kind of view, you can already see if the dimension is getting to 2, you will never find a beta such this sum will converge. So that's why this is pointing out that there's just with this special regularity we want to have, it's just possible in one dimension. Yeah. Now I still have more slides, but I was really clean. Okay, I just try to briefly sum it up. What's the main idea of the finite element? Because I think most of you are familiar with what we are doing. So we are searching now for the finite element spaces, which contain, in our case, of continuous piecewise linear functions. So we really decided to use just linear function, not polynomials or somebody else. We can use this to get a better order of convergence, but then we need more assumptions on the regularity. And now what we're just doing, we take a orthogonal projection given by this scalar product. It's just a normal way, and we approximate like every operator by a finite element version. And then we know that the solution is already given by these things I here pointed out, also the strongly continuous semigroup, which is the same, but this way just discretized. You can just compute it by using the exponential matrix expansion. It's a simple calculation. I just think I skipped this because I just have some more minutes left. What I wanted to show you is here some kind of our approximation results. So as we know, the noise is the key factor. We can just here see how fast the noise involves in our linear stochastic equation. So we start with a cosine something initial condition, and then we see here like step by step how the solution changed, and it's really getting influenced really fast. So that's what you see there is really white noise. Yeah, that's what I wanted to point out. I can also think I can maybe just say some more words about the approximation of noise. So what we are doing, we consider our new Wiener process or projected new Wiener process as a pH Wiener process. My goodness. And there are several options. We decided for the second options, we decide to solve the eigenvalue problem just on the finite element space. And then we present as a such kind of series so we just get the discretized series representation. Those who have worked with Wiener processes know this is the normal representation of a Wiener process. Just we truncated this process already at NH. And yeah, I think I'm already over time. So I just put it here. And I want to say thank you for your attention. I hope I got your not too confusing part. I was a little bit confused by this. Yeah, and I'm happy to answer your questions.
Questions, comments? Well, I'm not such an expert in software GPs. But my question is, let's say, from the mathematical point of view, as far as I understood, the math result is existence of big solutions or mild solutions, right?
Yeah, that's the idea.
And then in order to, of course, you want to compute something, you make some numerical method, numerical approach. Do you need for this numerical approximation? Do you need the existence of a mild solution? You don't need, right? You can just do numerics.
Yes, for sure. We can just do it. It's also like the physicists have done this in their paper. They never thought about the existence of a solution of such kind. But as we are mathematics, we want to know, and that's what's interesting to learn about this type of solutions. But yeah, you don't need it, but it would be nice to have it before.
So, if not, thank you very much again. We have a okay. Yeah, okay. Okay. So let us continue with our program. Next speaker is Stefan Steuerbeck from Almaty. The title is Ethical Exponents for the Equations is combined nonlinearities. So please.
Thank you. Thank you very much. Good morning, dear participants, dear guests. I hope today we will the last talk about Fujita critical exponent within this conference, because the last week we had 4 lectures about this subject, and but today we will a little bit different subject, because here we have not just power law nonlinearity, and here we have combined nonlinearities. And before starting my talk, let me share some quick announcement about the conference, which will be held next year in Astana, in capital of Kazakhstan. There will be the Isaac Congress. Isaac is the International Society for Analysis, its Applications and Computation. It will be from 21 to 25 July 2025 in Astana. Astana is capital of Kazakhstan and in north part of Kazakhstan. And this is the first Isaac Congress was started in USA in 1998 in Delaware, and the later second one was in Fukuoka, Japan in 1999, and also third one was in Berlin, Germany in 2001, and after that in Toronto, Canada, 2003, and in Italy, 2005, and also in Ankara, Turkey. And later, seventh Congress was in London, UK, and the next one in Moscow, and also in Poland, in Krakow. Also, 10th Congress was in Macau, in China. Also in 2017, next one was in Sweden, and also in Portugal in 2019, and in Ghent, Belgium in 2021. And the last one was in Brazil in 2023. And next one will be in Astana, and we have this kind of a lot of nice speakers. Here, Manuel Delpino from University of Paz. He's member of Academy of Science in Chile. He's an expert in nonlinear analysis. And Hongji Dong from Brown University, USA. He's also expert on PDE. Also, we have Yoshikazu Giga. He is a quite famous man in Japan. He is also expert on PDE. And here we have Martin Heyer from Switzerland. He is Fields Medal laureate. Yeah, he's expert on stochastic analysis. And also we have Carlos Koenig from USA, University of Chicago. He is also a very famous man. He was president of International Union of Mathematics. He is also expert on nonlinear analysis. And we have Ari Laptev from Imperial College, UK. He's expert on spectral theory. Also, Alexei Mailbaev from Brazil. He's expert on fluid mechanics. Nader Masmoudi from Current Institute. He was a PhD student of Pierre Lyons. He's also a very nice expert on the field of PD and fluid mechanics. We have also Mette Sonner from Princeton University. He is expert on geometric measure theory and financial mathematics. Also from University of Cambridge, Carola Bibiana Schönlieb. She is expert on numerical simulations and numerical analysis. Also, we have Susanna Terracini from Italy, University of Turin, and Gang Tian from China, Peking University. He's also very famous mathematician. He's an expert on differential geometry. And also we have 21 special sessions. And first one, organizing by me and Monica Musso from University of Baz. And there is also travel grants for young mathematicians, 35 years and younger. And I invite everyone to participate on this event and again, come to Kazakhstan, visit north part of Kazakhstan. And now let us move to the mathematical part of our presentation. Let us consider this kind of quasi nonlinear parabolic equation given by the formula 1. Here we have ut, Laplace p is the p Laplace operator, and here we have power law nonlinearity, also gradient nonlinearity, and also we have here forcing term, and here lambda and mu real numbers, alpha and beta positive numbers. This one is p Laplace operator, represented by this expression. And sure, we were interested on the critical behavior of this problem about the global existence and about the blow-up solutions. And let us briefly show some historical informations and some particular case of this problem one. And P, when P equal to 2 and the lambda equal to 1 and the mu is 0 and forcing term is also 0, then this problem coincides with a problem which considered by Hiroshi Fujita in 1966. This semilinear heat equation. And he proves that the critical exponent of this problem can be written in this form. It means that when alpha between 1 and 1 plus 2 divided by n, then there is no positive in time global solution for any positive initial data. And when we grid then this number, then for sufficiently small initial data, there is global in time positive solution. And later in 1983, Soviet mathematician Viktor Galaktionov considered the P-Laplacian extension of Fujita's problem. Instead of a Laplace operator, he considered this kind of P-Laplace operator and interested on the critical behavior of the solution. And he found that the critical exponent in the sense of Fujita can be presented by this expression. Later, in 1999, Zhang considered with forcing term this kind of semilinear heat equation with forcing term, but with Laplacian. And he also found another type of critical exponent. And here, in one-dimensional, two-dimensional case, the critical exponent equals to infinity. Starting with three-dimensional case, it can be written as this one, n divided by n minus 2. And yeah, in 2007, Zeng considered the P-Laplacian extension of the Zhang results. And he also found this kind of critical exponent. When n less than p, then the critical exponent will be infinite. When n greater than p, then there is a critical exponent like this. P minus 1 n divided by n minus p. In 2006, Philippe Souple and Jean consider this kind of semilinear parabolic equation with forcing term, but with gradient nonlinearity. And he proved the following results. Here only global solution, but when beta between 1 and n divided by n minus 1, then when t goes to infinity, the solution of this problem will be infinite also. But if beta greater than this number, n divided by n minus 1, then this term, when t goes to infinity, then this norm will be finite. In both cases, we have a global solution, but in the first case, it can be gross up to when t goes to infinity, but in the second one, it's bounded. And stationary version of this problem was considered by Hanson, Mazia, and Verbitsky. Stationary version, I mean elliptic case of this problem. And they prove that within this range, there is no solution of elliptic problem. But in this case, there exists positive solution of elliptic problem. This part. Yeah. And in 2019, Tayachi and Zak, they consider the same problem as we consider, but without forcing term, but with classical Laplace operator. And later in 2020, Gileli, Samet, and Souple, they consider with forcing term. And in this paper, second one, they prove that if alpha between this range, 1 and n divided by n minus 2, or beta satisfies this property. First case, if alpha between these numbers, then beta will be any positive number greater than 1. And also in the second one, if beta satisfies this property, alpha will be any positive number greater than 1. Then for any initial value from this space and the forcing term from this space, and if forcing term satisfies this kind of property, then the solution of the problem 1, in this particular case, p equals to 1, equals to 2, there is no global in time positive solution. It means that there is a blow-up solution, blow-up infinite time solution. From here, we can conclude that the critical exponent discontinuous. First one, if alpha between this beta can be any number, then p is finite. Or beta between this range for any alpha, also t is bounded. They will also blow up. And they also prove that if alpha and beta greater than these numbers, then for sufficiently small initial data and the forcing term, there is a global in time solution of this problem. And this is blow-up case. And the global existence case only for this range, n greater than n minus 2, and beta greater than n divided by n minus 1. Then p is infinite. The solution is global, exists. And if you mention here also, if you note here, also the critical case is not investigated and was left open. Then the main goal of our presentation, first extend these results for the P Laplacian case, and also prove the critical case also. And let us formulate our first main result. This result was published in 2023 in Journal of Evolution Equations. Suppose that U0 and the forcing term from this space, it's bounded and integrable function. Also suppose that beta and alpha greater than maximum value of these numbers. Lambda and the mu is strictly positive. And if integral of f strictly positive on Rn, and if alpha and beta satisfies this property, alpha less than this number for any beta, or beta less than this number for any alpha, then our problem does not admit global in time positive solution. Global in time solution. And in second case, supercritical case, if n greater than p and the alpha greater than this number and the beta greater than this number, then for sufficiently small initial data and forcing term, some positive forcing term, there is global in time solution of this problem. And from here, it follows that here also the critical exponent is discontinuous, but if beta greater than critical exponent, yeah, then we have the same result as the case without gradient term. Because here, if alpha satisfies this property, then T is finite. And if alpha greater than this number, then the T is infinite. And in the second case, if beta less than this number, critical exponent, and alpha any positive number greater than 1, then T is T is finite. So in first case, if beta greater than this number, and for alpha, this kind of alpha, we have blow-up result. And if alpha greater than this number, then here we have global existence result. In the second case, if beta less than this number, for any alpha, there is no global in time positive global in time solution of this problem. From here also follows that if P equal to 2, then our theorem completes the results from this paper, Gileli, Samet, Souple, the critical case. And now let us consider the Lie type second critical exponent. Here we suppose that n greater than P, alpha greater than this number, and the beta also greater than this number. Now we consider the case when we have global existence for sufficiently small initial data. And let us define this kind of sets, I r plus and I r minus. Here we suppose that f, this forcing term, bounded from below by this kind of polynomial for sufficiently large x. And in the second case, we suppose that f bounded from above is the same polynomial for sufficiently large x. And let us formulate the second result. And also suppose that initial function is bounded and integrable function, n greater than P, alpha greater than this number, and beta also greater than this critical exponent. Then if this forcing term belongs to this set, I r plus, and r satisfies this property between 0 and the maximum value of these numbers, then the problem 1, quasi-linear parabolic equation with gradient nonlinearity, does not admit global in time positive solution. And in the second case, if n greater than P, and if maximal value of these numbers less than r, but r less than n, then the problem 1 admits global solution for sufficiently small initial data and some positive forcing term from this set. And the third case, suppose that f from this set, I r plus and r is non-positive number, then the problem 1 does not admit any global in time positive solution. And this second result is a new even for the case classical Laplace operator. for any P greater than 1. Okay, we will skip the proof, but let us briefly discuss about the proof of this theorem. The subcritical case is not difficult. It can be proved by a standard test function method. But the critical case, in the critical case, we use our approach. It's also test function method, but with logarithmic argument test function. And also, supercritical case will be proved by comparison principle. We can construct some solution of elliptic equation, and this stationary solution will be also the stationary solution of our problem. It means that our solution is not blow up when when alpha and beta greater than critical exponent. Yeah, this approach was first time introduced in our paper, published in 2022. Later, we improve our approach on the different sets, like exterior domain, Heisenberg group, and also in Rn, also in Arnold's domain. And now, let us briefly give some new results. It's still unfinished. We consider this kind of Sobolev type equation with combined nonlinearity also. Now we are studying this problem together with Philippe Souple. And today, for now, we have only some partial results. And this problem, when we consider without forcing term, it was first time studied by Korpusov, Russian mathematician. And he proves that if P between this range, then the problem tree does not admit any local in time weak solution. Here, not global or local in time weak solution from this space for any arbitrary small t, capital T. And the later extension of these results on the Riemann manifold was studied by Gileri and Samet in 2023. And also on the Heisenberg group, here we have one paper. It was recently accepted in this journal. And let us give our partial result. Here we have only a result for non-existence case. And let us suppose that initial function from this space, here, this one is a homogeneous Sobolev space. When n equal to 1 and 2, one-dimensional, two-dimensional case, and for any p and q, there is no local in-time solution of this problem. And if n started with 3, then when p less than this number for any q, or q less than this number for any p, in this case also there is no local in-time weak solution of our problem from this space. Now we are studying the case when p greater than this number and q greater than this number. We expect that in this case we will get local existence of solution to this problem. Also, there is an interesting question about global existence case when p greater than this number, q greater than this number. And this is just a partial result. We hope we will finish this paper end of this year. Yeah, and it was the last page of my presentation. Thank you for your attention.
Are there questions, comments? What is non-local solution?
Not non-local, local and global. Yeah. Yeah.
Okay, but I understand. Thank you very much again.
Thank you.
This one. That's something to be very. Your information is that 1 half an hour is mentioned and then that will be 15 minutes. Half an hour, then and then you go to the 15.
Yeah.
The next speaker is Wahya Gaines from Wilmenau. The title is a bit point. If it's a quick idea from the middle of play, this is conception.
Good morning. First of all, I would like to express my deepest gratitude to organizers of this conference for a very warm and friendly atmosphere. I would talk about a classical, I think, topic about limit point and limit circle criteria for ordinary Sturm-Liouville operators with complex coefficients. It is a joint work with my colleagues, Edison Leguizamon, Carsten Trunk, and Monica Winkelmeier. And the biggest part of this work belongs to my colleagues. We consider a Sturm-Liouville differential expression in a general form. Here, W is positive real function. P and Q are complex functions. P is not equal to 0 almost everywhere. And 1 over P, Q, and W are locally integrable functions. So we consider our differential expression on the half line, and to be locally integrable on the half line means that the functions are integrable on each compact subinterval of this half line. We make the following assumption. We introduce a set Q. It is a closed convex hull of such a, excuse me. Yeah. 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 We introduce the following set is something like numerical range of operator, but we don't give any explaining here, but something like this. Assume that this closed convex set don't equal to complex plane. And we can, without restriction of generality, assume that 0 belongs to the boundary of this set Q. Then there exists an angle such that we can rotate our convex set Q such that the image of this rotation will be lie to the right. So in the closed right semi-plane. This is expressed by this condition. We are interested in the study of solution space of homogeneous equation. This will be helpful in many questions of spectral theory. First of all, deficiency indices of our operator, resolvent, and so on. Yeah. Introduce the following Hilbert spaces. H theta is the space of all absolutely continuous locally absolutely continuous functions such that this norm is finite. It is obvious that the space H theta is a subspace of our natural Hilbert space H. By nature, I mean weighted L2 space over Y with weight W. This theorem was obtained in